Right now, over 28,000 tracked objects are zipping around our planet at roughly 17,000 miles per hour. Nearly 9,000 of those are pure dead weight, defunct satellites, spent rocket stages, and jagged shards of metal. Earth's orbit currently operates as a highly congested, hyperspeed highway. Modern aerospace engineering has successfully addressed the influx of new waste. Reusable launch vehicles, like the Falcon 9, are designed to return to the surface rather than shedding disposable stages into the void. This preventative architecture stops the pile from growing, yet it leaves the existing legacy of debris untouched. This debris circles at the exact altitudes where our most critical infrastructure operates, from the International Space Station today to upcoming commercial modules like Vast Haven and Starlab tomorrow. Billions of dollars of hardware and human lives must constantly navigate a high-velocity minefield. The ultimate threat is the Kessler syndrome. If two large objects collide, they shatter into thousands of smaller, untrackable projectiles. Those fragments then rip through other satellites, generating even more shrapnel, until low Earth orbit becomes an impassable zone of destruction. Humanity's entire space-based economy currently balances on this knife edge. Keeping these orbits usable requires immediate active intervention to remove the largest hazards before the first collision triggers the next. Catching a dead satellite presents a brutal physics problem. You have to capture an uncooperative, rapidly tumbling object in a zero-gravity, frictionless vacuum. The volume of traffic is only going to grow. As we establish off-world industries like asteroid mining and lunar resource extraction, the density of heavy spacecraft transiting through Earth orbit will increase exponentially. To secure these transit routes, engineers are developing active debris removal, or ADR. These specialized spacecraft are designed to hunt down the most dangerous pieces of space junk and physically drag them out of the sky. The time for purely observational research has passed. Securing these orbits now requires the physical intercept and removal of hazardous mass before it shatters. Long before an ADR spacecraft ever reaches the launch pad, the target has to be identified. Organizations like NORAD use networks of massive radar dishes and optical telescopes to monitor the sky, tracking objects down to a single centimeter in size. Raw observation data feeds into mission control centers, where supercomputers map the distinct paths of all 28,000 tracked objects. They run continuous simulations to predict exact collision overlaps days or weeks in advance. But the biggest hurdle to cleaning up a target involves international law. Under current treaties, a defunct satellite remains the sovereign property of the nation that launched it. Touching or capturing a piece of hardware is strictly forbidden without diplomatic clearance. Before an ADR mission can solve the physics of a capture, it must first survive this gauntlet of microscopic tracking data and complex diplomatic negotiations. Once a target is cleared, the ADR spacecraft executes a rendezvous maneuver. It fires precise thruster bursts to perfectly match the target's speed and trajectory, bringing their relative velocity to exactly zero. For intact targets, missions like ESA's Clear Space 1 use robotic arms to grapple the dead satellite. Bumping it in a frictionless vacuum sends it spinning. The arms must close simultaneously, locking on to stabilize the cylinder without applying uneven force. Rigid arms fail on violently tumbling debris. For those targets, engineers use tethered nets. The net avoids direct rigid contact. The flexible tether absorbs the kinetic energy, slowly pulling the chaos to a halt as the line goes taut. Looking ahead, future satellites will be launched with disposal in mind. Missions like Astroscale's ELSA DAD are testing servicing, where ADR vehicles latch onto cooperative satellites using pre-installed magnetic docking plates. Because an old rocket booster degrades entirely differently than a shattered solar panel, engineers rely on a diverse toolkit of specialized, bespoke capture mechanisms. Once the target is secured, the final phase begins. The most straightforward method is using the ADR vehicle's own propulsive engines to physically drag the captured debris out of its stable orbit. To conserve fuel, the spacecraft can deploy a massive drag sail. This increases surface area to catch sparse atmospheric particles high in orbit. The resulting friction is enough to decay the orbital path, pulling the spacecraft into a downward spiral. Satisfied, whether by thruster or by sail, the end result is the same. The captured debris is dragged into a controlled, fiery re-entry. vaporizing in Earth's atmosphere and permanently neutralizing the threat. For decades, low Earth orbit was treated as a passive dumping ground. The current data dictates a new reality of actively managed orbital sustainability. These ADR technologies serve the same purpose as terrestrial waste management. They are the essential street sweepers required to keep the orbital highway functional. As the International Space Station retires and commercial habitats scale up, maintaining a clean environment is the only way this new space economy can operate. Active debris removal has moved from the realm of speculative engineering into a core operational requirement. It is the foundational maintenance that ensures low Earth orbit remains a safe and navigable zone for all future spaceflight.